Okay, this lesson is on graphing rational functions. Rational functions are functions that are ratios or fractions. So you can see in these examples here, you have functions that are fractions. So you have variables on the top and the bottom. Now, when you graph rational functions, some interesting things happen. So what we're going to do is look at the graph of the rational function first. And Desmos is going to come in pretty useful in this lesson as well. So one of the things I want you to do first is go ahead and put the first equation into Desmos, and I will do the same. So we have 2x divided by x squared minus 1. Alright. So what we see here, and I'll try to show this on the graph here. What we see here is a very interesting graph. It's got 3 different pieces, but what we see here are these gaps. You see a gap right there, and you see a gap right here. If you really smush the graph, sort of smush, and then you stretch out the x-axis, smush, you can really get a sense of these sort of discrepancies here in the graph. These are called vertical asymptotes. One of the things that you have to remember, so I'll put that over here. One of the things that you have to remember with fractions is we cannot have 0 in the denominator. Remember back, I don't know when you learned this, but a while ago, you can't divide by 0. You can't. It's impossible to divide by 0. You can't cut something into 0 pieces. So we cannot divide by 0. So any number that will give us a 0 in the denominator makes the function invalid. So in Desmos, you see those as gaps in your graph. So looking for those gaps, now you might be able to figure out where those gaps are just by looking at them, but sometimes it's not so obvious. So what we need to do is figure out what makes the denominator 0. And that will tell us where these gaps are. So that is what vertical asymptotes are. Vertical asymptotes are gaps in your graph, when you get a 0 in the denominator. In the denominator. And it happens when it's 0. Oh, I'll just cross that. So how do we figure out what numbers are going to give us 0 in the denominator? Well, we can do this pretty simply by just setting the denominator equal to 0. So if I take the denominator, x squared minus 1, and I set it equal to 0, I can figure out what values of x are going to give me 0. So I add the 1 over, so I get x squared equals 1. I then can square root both sides, give me x equals plus or minus 1. So what that tells me is that there is going to be a gap at positive and negative 1. And if we return our graph back to the screen here, we can see that, yep, there is a gap at negative 1 and a gap at positive 1. So how does that look like on our graph? Well, we have a graph like this. Vertical asymptotes, well, any asymptote for that matter, is expressed by a dashed line. positive 1 and negative 1. And they're vertical, obviously, because these are vertical asymptotes. So we're not going to get into the graphing piece. I just want to show you what those vertical asymptotes look like. Let's try another problem. Again, to find out where our vertical asymptotes are, we're going to set the denominator equal to 0. So x squared minus 3x plus 2 equals 0. Now this one's not so simple that you could just solve for x. This one you're going to have to factor and then solve. So we think about what numbers multiply to be 2 and add to be negative 3. Okay, we can factor this just like this. What numbers multiply to be 2 and add to be negative 3? We should have guessed negative 1 and negative 2. So x minus 1 and x minus 2. Those multiply to be positive 2 and add to be negative 3. We set them equal to 0, giving me x equals positive 1 and x equals positive 2. So what that means is I'm going to have vertical asymptotes at 1 and 2. So on the graph, I draw a dashed line at 1 and a dashed line at 2. And if you want to, you can put it into Desmos and verify those answers as well. So that's what our vertical asymptotes. You set the denominator equal to 0. Which brings us to our next piece, domain. You might remember domain from back in freshman year. Domain is a list of all the x values. If you remember, domain is x. Domain is all of the x values. The problem is that if we look at this graph, okay, let me return it back to normal. So that's what it looks like normally. If domain is all the x values, this line goes to negative infinity, and this line over here goes to positive infinity. I would take forever to write all the numbers that are included in this domain. So sometimes it's easier to write the domain on what numbers it can't be. Now remember, x can be a lot of numbers. But what are the only numbers that x cannot be? It can't be 0 because that makes your function invalid. So what numbers, what values of x make your denominator 0? Well, in this case, it's 1 and negative 1. So domain will be all real numbers except vertical asymptotes. Whatever those are. All numbers except vertical asymptotes. All real numbers except vertical asymptotes. So, we could find the domain. So the domain here, if we set the denominator, I'm only going to do one of these, but if we set the denominator equal to 0, so x squared plus 9x plus 20 equals to 0, we factor this. What multiplies to be 20 and adds to be 9? Well, you should have got 4 and 5. X plus 4 and x plus 5. So when we set them equal to 0, we get x equals negative 4 and x equals negative 5. So what that means is that the domain would be all real numbers except for negative 4 and negative 5, because those are the only numbers that would make the function invalid. So that's vertical asymptotes. Now, let's look at horizontal asymptotes. Yes, you do have lines that go across your graph of y values that it cannot be also. Let's return our original graph here. Okay? If I smush the graph once again, do you see maybe a y value that it cannot be? Maybe something that, this line is approaching but never getting to cross, or on this side, this line approaching but never ever getting to cross? Well, if you guess 0, that's right. In this case, 0 is your horizontal asymptote. Horizontal asymptotes are are horizontal lines that at the ends of your graph they cannot cross. So there are several types of horizontal asymptotes. Okay. Let's see here. Get that brighter. There you go. Horizontal asymptotes are limits at the edges of your graph. They're limits at the edges of your graph. So when you look at the edges, not in the middle, we're looking at the edges of the graph, the far right or the far left. What is the limit of your graph? Where is it not being able to reach? It's going there and it's trying to get there, but it just can't get there. There are two different ways, two different types of asymptotes that we will see as far as horizontal. I know I have 3 bullets here because there is a third way. It just doesn't happen in Algebra 2. It happens in pre-calculus if you end up going there. To find your horizontal asymptotes, we look at the degrees of the top and the bottom of your function. So we look at the degree of the top, which here is a 1, and we look at the degree on the bottom, which here is a 2. If the degree on the bottom is bigger than the degree on the top, so this case right here, where you have an x squared on the bottom, is bigger than the x on the top. If bottom degree bigger, if bottom degree bigger, then y equals 0 is asymptote. Okay, so if the bottom is bigger, like in this case here, the bottom is bigger than the top, you have a horizontal asymptote at y equals 0. It's automatically 0. It doesn't matter what anything is in the bottom or the top. If the degree on the bottom is bigger than the degree on the top, then it's automatically y equals 0. And that's exactly what we saw in our original graph here. If we look at this, notice the equation. The bottom has a squared and the top is just an x. The bottom is bigger. So when we look at our graph, you see that the limits at the edge of the graph is a y equals 0 line. Now we don't care about the middle, we care about the edges. It doesn't cross 0, it doesn't cross the x-axis. And so that's the limit, and that's the horizontal asymptote. Right? The other type of asymptote is, well, what if they're the same? So if top and bottom degree are the same, then ratio of coefficients is asymptote. Now, what do you mean by that? Well, let's take, for example, this one right here. Notice how they're both x squareds. Okay, so in this case, they are the same. So we use the second rule here. If they are the same, then the ratio of coefficients is the asymptote. So here we look at the coefficients of those degrees. The top is a 2, the bottom is a 1. So it's 2 over 1. So in this case, because they're the same, the asymptote is 2 over 1, or 2. Y equals 2. Whereas in this one, the bottom is bigger, so this is automatically y equals 0. So let's look at this and put it all together. We're going to graph this one here. Okay. Y equals x plus 2 over x minus 2. First things first, let's find the vertical asymptote. The vertical asymptote exists where your denominator is 0. Now this one's pretty easy because it's already sort of in a factored state. What x value makes my denominator 0? Well, it's 2. So my vertical asymptote is at x equals 2. I'll call this VA. It's at x equals 2. So I go down here on my graph at x equals 2, and I draw a vertical line. Now you won't always have 2. Sometimes you only have 1, so just so you know. Now we find the horizontal asymptote. Horizontal asymptote, you look at the degrees. Now in this case they're the same. They are the same, so you look at the coefficients. Well, the coefficient here is 1. The coefficient here is 1. So it's 1 over 1, or y equals 1. So that means that on our graph we have a horizontal asymptote at y equals 1. Like that. Now we have to fill in the graph. Now here's where Desmos comes in. So we're going to take our graph here. Let's zoom out a little bit so we can see everything. And I'm going to put into my function here the y equals, I think it was x plus 2. Yep, x plus 2. X plus 2. Now some of you might be thinking, oh, I don't have to put y equals. You don't have to put y equals. X plus 2. Some of you might be thinking that, come on, there you go, x plus 2. Mr. G, how do I get to the bottom? How do I put that all over and put stuff at the bottom? You just add some parentheses, just like that, and then hit divided by an x minus 2. So you can see on our graph that we do have that gap. Now let's smush the graph here and verify our asymptotes. There's our horizontal asymptote at 1. See right here it's at 1, so on the edges it's not crossing 1. And we also have a vertical asymptote. If we smush this graph like this, you can see here at 2 we also have the vertical asymptote. So our graph is correct. So now how do we actually graph this? Well, there's a tool here in Desmos that'll help us get some points. By clicking the gear here at the top and switching to a table, we get points. We get some points to plot. Now you just need points on both lines. So you'll see here I only have points on this line. So if we want points over here, I'm going to have to go over 2. So like maybe like 3 or something like that. And so I can get some points there. So here's all my points. So all I do on my graph is I'm going to go and actually put these on the graph. Zoom in. Okay. So I have a point at negative 2, 0. So negative 2, 0 is a point right there. I have a point at negative 1 and 0.333333. Negative 0.333. I have 0, negative 1, 1, negative 3. So you get an idea of where it goes. Now you just go up to the limit there of the horizontal asymptote and connect the dots. On the right side over here, I have a point at 3, 5. So that's 1, 2, 3, 4, 5. And you follow sort of the same pattern. Making sure not to cross your horizontal or vertical asymptotes, especially the horizontal ones at the edges. And that's it. That's graphing rational functions. Let's try one more. Let's try number 2. So here, again, vertical asymptote first. Okay. Vertical asymptotes are what makes your denominator 0. In this case, it's real easy. It's already set out for you. So what makes the denominator 0 would be an x value of negative 4. So x equals negative 4 is my vertical asymptote. The horizontal asymptote since these are the same, we look at the ratio. It's 2 over 1. So it'd be y equals 2. Okay. So we're going to put this on our graph. So I got a vertical asymptote at x equals -4. A horizontal asymptote at y is 2. That. And now I just fill in the graph. So I go back over to my graph here. And I'm going to put in the function 2x minus 1, 2x minus 1. I'm going to use parentheses so I can get to the bottom. And x plus 4. And when I look at my graph, zoom out a little bit, I can see that vertical asymptote, or horizontal asymptote, sorry, is at 2. So you can see there the horizontal asymptote is at 2. I can also figure out my vertical asymptote is at -4. So we can verify that. So let's return home now, and this is what it sort of looks like. So now I want some points. So I click the gear, click the table, and there are some points. Notice that all of them are on this line, so I will need some ones over here past -4, so maybe like -5. So there's a point over there too. So now I'm going to plot all of these points onto my graph. So I have -2, -2.5. I have -1, -1. 0 is -0.25. You get the point. You don't need to draw all these points here. You only need one. And then the one I have on this side is at -5 is 11. So -5 is actually like off my graph. But you do basically the same way the other one is. And that's it. The last thing that we have is now on the third page. And that is holes. Holes are interesting because if an asymptote acts like a wall, we saw like on the graphs, like the vertical asymptotes are walls, like the graph can't physically cross them. Think of a hole as like a door. You have this wall, but there's this one part where you can get through, and that is a hole. So holes exist in graphs where both top and bottom of fraction are 0. Where both the top and the bottom of the fraction are 0. So what values of x would actually cause it to be 0 over 0? Now you can't divide by 0, but an even weirder concept is 0 divided by 0. So that's where holes will exist. Now I'll show you the long way of doing this, and I'll show you the very, very easy way of doing this. Essentially, we would have to figure out what makes the top and the bottom 0. So we would have to factor both of these. So let's get a close look at this equation here. So the top, x plus 3, so what multiplies to be -28 and adds to be 3? Well, what multiplies to be -28 and adds to be 3 is 7 and -4. So x plus 7 and x minus 4. What makes the denominator 0 is what multiplies to be 35 and adds to be 12. What's 7 and 5? So I'll do it down here, x plus 7 and x plus 5. You'll notice that you have the same factor on the top and the bottom. Okay, that means that the same value is going to make it 0 on the top and the bottom, and that value is at -7. So we know that we're going to have a hole at -7. Now, putting that aside, let's actually graph this problem. So we start off with our vertical asymptotes. Our vertical asymptotes are what makes our denominator 0, and that is, if I set these equal to 0, x equals -7 and -5. Both of those values would make the denominator 0. Horizontal asymptote is the degree of the top and the bottom. Now these are the same, so we look at the coefficients, which is 1 over 1, or 1, y equals 1. Let's throw in their domain, because we haven't talked about that in a little while. Domain. Domain is always all numbers except your vertical asymptote, so except -7 and -5. Now, holes. We know that a hole, and I'll just put it down here because I don't have any more room. There should be a hole at x equals -7 because that is what matches on the top and the bottom. But I'm going to show you how you can actually find holes without actually doing any math. So, let's graph our asymptotes and then we'll go ahead and graph our lines. Vertical asymptote at -7 and -5. So right here, -7 and at -5. This is going to be real smushed. And a horizontal asymptote at 1. This is going to look sort of weird on a graph, so let's look at this on a graph. So I'm going to put this into Desmos. I have x squared plus 3x minus 28 all over x squared plus 12x plus 35. Okay. Let's zoom out here. Now this looks weird. Desmos has a hard time with this. One of the things that will signify that you have a hole is when one of your vertical asymptotes is missing. I'm going to change this to a table view so we can see this. So, did I put something in wrong? Looks weird. Minus 28. Oh, that's why. Plus 12x. I was like, this looks weird. Hey, there we go. Okay. So, one of the things that will signify that you have a hole is if one of your asymptotes is actually missing. So I should have two. I should have two gaps. I should have a gap at x is -7 and x is -5. But when I smush this down and I look at the graph, I only see the one at -5. And so let's zoom in here so you can see this. Okay, see here in the middle, I only have the one at where's the one at -7? There should be one right here. I should have a vertical asymptote right here, but it's not there. So that's what tells you you have a hole. You don't have to do the math and actually figure out what makes the top and the bottom 0. Look at your vertical asymptotes. You should have one at -5 and -7, but I don't. I only have one at -5. The -7 one is missing. What that means is you have a hole at -7 because it's gone. It's not there. So when we go to do our graph on here, the -7 asymptote is actually missing. It's not there. So you're going to have your line go right through it. Think of this asymptote as being there, but there's a door. Okay, and that door allows the line to go right through the asymptote. So when we go to graph these, we have a few things we need to, a few points we need to graph. I'm just going to look at a table on mine, and you can look at a table at yours. Basically, -6 is -10. It's like down here. And then let's do -7. Oh, that's because that's undefined. -8 is 4, so -8 is 4. So you can see here, and let's even do -9. -9 is 3.25. So you can see here that this graph actually just goes right through the asymptote because there's a hole. There's a hole somewhere right here. There's a hole. Okay, and on the other side, I have -2 is -2. We'll do 0 is -0.8. Yeah, so you have a graph that looks like this. And I actually did this. This is not right. Sorry, guys. You're probably like, what the heck? That's not how mine looks. Like, it's on the other side. Negative, this is +10. Sorry. And -8 is +4. Jeez. It's a mess. Here we go. That's what it should look like. And then there's a hole somewhere right there. That's how your graph looks. Okay. So, what we're going to do is you're going to practice, go all the way through on number 2. Go all the way through. Find your vertical asymptote, find your horizontal asymptote, write your domain, see if there's any holes. Remember, you don't need to do that mathematically. You can just look at the graph and graph it. Go ahead and pause the video when you're ready. Or pause the video, try number 2, and hit play when you are ready. Okay, so vertical asymptote. You should have vertical asymptotes at x equals 2 and -1. Sorry, -2 and +1. Horizontal asymptote should be at y equals -1. Okay, and then that makes your domain. So domain is all numbers except -2 and +1. On a graph, what this looks like is you have one at -2 and at +1. You have a horizontal asymptote at -1. Wow, that's a terrible line. And then you'll find that you actually have a hole. This one here isn't actually visible, so you have a hole at x equals 1. Because this asymptote on your graph, if you're to graph this in Desmos, this is actually not there. That tells you that there's a hole there. So, and then when we put this in table form, we're going to plot these points. I got -3, -1, 2, 3 is 0. You only need 1 point at each thing. So I know that based on my graph, it goes like this. And then in between, I have one at -1 and -2. -1, -2. And 0 is -1.5. So remember that in the middle, yours can cross the horizontal because it only affects it at the edges. And then the last one is 2 is negative 1.25. And then, so I have one that goes like this. So that's what it looks like. It doesn't have to be fancy, but it should be accurate, meaning that you have at least 1 point on each line. And that's it. That's an entire problem from start to finish. Vertical asymptote, horizontal asymptote, domain, holes, if there are any. Sometimes there's not. Sometimes all of your asymptotes are there. Okay, and well, I don't know what the heck. This is not. Jeez. Sorry. This is what happens when you go fast. That's not supposed to be like that. It's supposed to be like this. Sorry. Sorry, trying to go too fast. But your bottom line here should look like that. Okay. Not like what I did up here. But you get the idea. If you have any questions, please stop and ask me and I can go over this with you. Sorry for the long lesson, but graphing polynomials is a lot. If you need help, let me know. Thanks.